Hello, this is Dr. Joe Angley. Today we're going to be learning about the greenhouse effect. After viewing this presentation, we'll have a short assessment to see how well you did with the material. Today, the issue of climate change is almost continuously before us, in the news, in our culture, and as an important political issue. Politics aside, most scientists now understand that our climate is closely linked to how humans use fossil fuels. The important characteristic of fossil fuels is that when we burn them, we release carbon dioxide into the atmosphere. In this presentation, we will learn what effect all this extra added carbon dioxide has on our planet. So, our overall learning objective is to understand what the greenhouse effect is and how it affects our climate. We will also be learning about terms such as weather, climate, and the concept of reflectivity. We also want to understand how greenhouse gases like carbon dioxide exert such an influence on our climate system. Clean, dry air is 78% nitrogen and almost 21% oxygen, with the remaining 1% composed of argon, carbon dioxide, and a variety of other gases. Water vapor varies from near 0 to 4%, depending on air temperature and available moisture. Minute particles and liquid droplets, collectively called aerosols, are also suspended in the air. Atmospheric aerosols and water vapor play important roles in the Earth's energy budget and in rain production. In the next slide, we'll look at the composition of the atmosphere in more detail. This slide shows the composition of the atmosphere. As I mentioned, the major gases in the atmosphere are nitrogen and oxygen. Take a look and see if you can find out how much carbon dioxide there is. The atmosphere has 4 distinct zones of contrasting temperature due to differences in absorption of solar energy. The layer immediately adjacent to the Earth's surface is called the troposphere. Tropine meaning to turn or change in Greek. Within the troposphere, air circulates in great vertical and horizontal convection currents, constantly redistributing heat and moisture around the globe. The troposphere ranges in depth from about 11 miles over the equator to about 5 miles over the poles, where air is cold and dense. Because gravity holds most air molecules close to the Earth's surface, the troposphere is much denser than the other layers. It contains about 75% of the total mass of the atmosphere. Air temperature drops rapidly with increasing altitude in this layer, reaching about negative 76 degrees Fahrenheit at the top of the troposphere. A sudden reversal of this temperature gradient creates a boundary called the tropopause. This temperature boundary occurs because ozone molecules in the stratosphere absorb solar energy. In particular, ozone absorbs ultraviolet or UV radiation at wavelengths of 290 to 330 nanometers. This absorbed energy makes the stratosphere warmer than the upper troposphere. The stratosphere extends about 50 kilometers or 31 miles out from the tropopause. It's far more dilute than the troposphere, but it has a similar composition except that it has almost no water vapor and nearly 1,000 times more ozone. Unlike the troposphere, the stratosphere is relatively calm. There is so little mixing in the stratosphere that volcanic ash and human-caused contaminants can remain suspended there for many years. As you can see from this figure, human activity like flying in an airplane, climbing a mountain, driving your car all take place in the troposphere. Also note that the ozone layer, which protects the planet from ultraviolet radiation, is located in the stratosphere, which is the layer above the troposphere. Now, to understand the effect of carbon dioxide and other greenhouse gases on climate, we need to make sure we understand the difference between climate and weather. Here I am in New York City, experiencing some cold weather. Weather is defined as short-lived local patterns of temperature and precipitation. And we know from looking at the weather reports that weather is constantly in flux. It may be hot one day and then very cool the next. This results from circulation patterns in the troposphere, which is that part of the atmosphere within which most human activities take place. We've been talking about weather, but I also want to mention another important word, climate. Climate is the average pattern of variation that occurs over a given region over long periods of time. One of the important things to understand about climate is that we don't expect it to change very often. Climate, when it does change, typically does so over hundreds or thousands of years. An example would be if I asked you, what is the climate in South Florida versus Boston, Massachusetts? You would certainly have an idea in mind. But generally you would know that Boston would be generally cold in the winter, whereas Miami would be much warmer. Climate represents these generalized patterns. The sun supplies the Earth with abundant energy, especially near the equator. Of the solar energy that reaches the outer atmosphere, about 1/4 is reflected by clouds and atmospheric gases, and another quarter is absorbed by carbon dioxide, water vapor, ozone, methane, and a few other gases. We'll see in the next figure. This absorbed energy warms the atmosphere slightly. About half of incoming solar radiation, or insolation, reaches the Earth's surface. Most of this energy is in the form of light or infrared or heat energy. Some incoming solar energy is reflected by bright surfaces, such as snow, ice, and sand. The rest is absorbed by the Earth's surface and by water. Surfaces that reflect energy have a high albedo, or reflectivity. Fresh snow and dense clouds, for instance, can reflect as much as 85 to 90% of the light falling on them. Surfaces that absorb energy have a low albedo and generally appear dark. Black soil, asphalt pavement, and water, for example, have low albedo with reflectivity as low as 3 to 5%. Here we see a table that shows us the reflectivity of various surfaces. If you've ever been out in the snow on a sunny day, you will remember that you often need sunglasses because it is so bright. Remember, surfaces that have low reflectivity, like blacktop or dark soil, absorb and re-emit long wavelength energy that we also call infrared energy. Here we see a diagram of the Earth's energy balance. As I mentioned before, the atmosphere absorbs or reflects about half of the solar energy reaching the Earth. The other half reaches the Earth's surface, and about 45% is absorbed and 5% is reflected back into the atmosphere. However, most of the energy re-emitted from the Earth's surface is long wavelength infrared energy. You can see this in the red-colored portions of this diagram. These long wavelengths are absorbed in the lower atmosphere, trapping heat close to the Earth's surface. The reason that infrared wavelengths are absorbed is because certain gases and aerosols in the atmosphere absorb and re-radiate most of this infrared energy, keeping the surface much warmer than it would otherwise be. This adsorption and re-emittance is known as the greenhouse effect. We call these gases that absorb and re-emit the infrared radiation greenhouse gases. The major greenhouse gases are water vapor, carbon dioxide, methane, nitrous oxide, ozone, and chlorofluorohydrocarbons, or CFCs. If our atmosphere didn't capture this re-emitted energy, the Earth's average surface temperature would be about 21 degrees Fahrenheit, rather than the current 57 degrees Fahrenheit. Thus, energy capture is necessary for liquid water on Earth and for life as we know it. The greenhouse effect is a common term to describe the capture of energy by gases in the atmosphere. Something like the glass of a greenhouse, the atmosphere transmits sunlight but traps some heat inside. Also, like a greenhouse, the atmosphere lets that energy dissipate gradually into space. The balance of the rate of incoming energy and outgoing energy determines the temperature inside the greenhouse. The policy issue that faces us is that we're slowing the rate of heat loss, thus increasing heat storage in our greenhouse. We are doing this by adding CO2, CH4 and N2O to the atmosphere at levels the Earth has not seen since before the appearance of humans as a species. The question is whether we'll be able to agree on changing this trend. This diagram helps explain why visible light passes easily through the atmosphere, but why infrared energy is blocked by greenhouse gases such as water, carbon dioxide, and ozone. This diagram shows atmospheric absorption and scattering at different wavelengths of electromagnetic waves. The largest absorption bands of carbon dioxide is in the infrared. This diagram demonstrates that the atmosphere is transparent to visible light, which we know because we can see. And here is the visible light. It also shows that carbon dioxide, water vapor, and ozone and other greenhouse gases absorb infrared radiation. This is why higher amounts of greenhouse gases absorb and re-emit more infrared radiation, trapping more heat in the atmosphere. The relationship between greenhouse gases and climate change has been known for some time. Svante Arrhenius, a Nobel Prize-winning physical chemist, developed a theory to explain the ice ages, and in 1896 he was the first scientist to attempt to calculate how changes in the levels of carbon dioxide in the atmosphere could alter the surface temperatures through the greenhouse effect. Based on information from his colleague Arvid Högbaum, Arrhenius was the first person to predict that emissions of carbon dioxide from the burning of fossil fuels and other combustion processes were large enough to cause global warming. The relationship between greenhouse gases, principally carbon dioxide, and temperature are demonstrated here in the Keeling curve. These data, derived from carbon dioxide and temperature readings from Mauna Loa volcano in Hawaii, clearly show that rising carbon dioxide levels are associated with an increase in temperature, as predicted by Arrhenius back in 1896. Measurements of atmospheric carbon dioxide taken at the top of Mauna Loa, Hawaii, show an increase of about 2.2% per year in recent years. Monthly mean carbon dioxide in red and average carbon dioxide in black track closely with the general trend in global temperatures, the blue line. The relationship between greenhouse gases and Earth's temperature has been further verified by analysis of ancient gases trapped in air from ice cores in the Antarctic. In these data, going back 800,000 years, there is a close association between temperature and carbon dioxide. As stated in the IPCC Fifth Assessment Report, human influence on the climate system is clear. The evidence shows unequivocally that climate is changing and the global average is warming because of increased retention of energy in the lower atmosphere. In this presentation, we've learned the difference between climate and weather. We now know that climate is a long-term pattern of temperature precipitation that occurs over long periods of time. In general, climate does not change quickly. We learned about the concept of reflectivity. Reflectivity is important in our discussions of climate because global warming reduces the amount of ice and therefore increases the absorption of infrared energy and reduces reflectivity, thus adding more heat to our climate system. We also learned that the greenhouse effect is a natural occurrence that makes the Earth habitable for humans. About half of the solar radiation enters the Earth's atmosphere and makes its way to the Earth's surface, where it's either absorbed or reflected. Long wavelength radiation is then radiated into the atmosphere, where some of it is absorbed by the greenhouse gases and re-emitted, thus warming the atmosphere. The problem with too much carbon dioxide and other greenhouse gases in the atmosphere is that it absorbs and emits more and more heat, warming the planet. Carbon dioxide concentrations, which have averaged about 278 parts per million over the last 800,000 years, are now consistently above 400 parts per million in the atmosphere, and global temperatures are expected to continue to rise. There are additional consequences to the increase in carbon dioxide, such as effects on the biogeochemistry of the ocean, and these we will cover in later presentations. Thanks a lot. I hope you learned a lot.